So far, we have gotten a brief introduction as to the concept behind the derivative, this tool that allows us to analyze the slope of a function by looking at kind of like this infinitely small rate of change that's going on between the change in the y value and the change in the x value on a really small scale. And without providing theory, I have just kind of given you this tool. And the first thing that we learned about using this tool was using the exponent rule, right? It was to take a polynomial like x cubed, and the derivative rule that we learned is that you bring down the exponent and you subtract 1 from the old exponent. And this is great. Right, this is just fine and dandy for a single polynomial term. In fact, we even learned how to do it for multiple terms, right? If we had x to the 6th plus x to the 3rd, then this would become 6x to the 5th plus 3x squared, because the derivative kind of distributes, if you will, term by term, and so on and so forth. And this is pretty much all we have right now. We've learned the basics of the exponent rule. But, as you can imagine, things get a little bit more complicated, right? There's all sorts of different functions that we encounter in mathematics. And so what we're going to be doing with these next few videos is really building our catalog and trying to go through all the different types of functions we could have, and figuring out how to take the derivative of each kind of them. Okay, now that sounds really daunting. But there's only really a few general rules that we need to know, and then no matter what the functions look like, we'll be able to apply them in some way, shape, or form. So, more or less, we basically learned how to take the derivative of kind of just one single polynomial term, one function, but it's very often the case that we get a product of functions. So, right, in algebra, it's very often that we get, something that looks like x cubed plus 7x squared multiplied by x minus 3, right? Things that kind of appear in factored form. And it'd be really nice if we had a shortcut sort of way to handle these problems, right? What happens if I tack on even more terms, right? And I have x to the 100th plus 2x cubed minus 17 x to the negative 3 or something like that, right? What happens when I have a product of functions? How do we tackle this? And so just to keep it simple, I'm just going to write down a little bit of theory real quick. So the product rule basically says, right, how the product rule works is that if you are given the product of two functions, okay, the product of two functions, let's call them f of x, and we'll call the other one g of x. Okay, given the product of two functions f of x and g of x, then the derivative of those, let's do the change in those functions with respect to x. So the derivative of the product of those functions, so of f basically multiplied by g, whatever those functions are, ends up equaling, right? There's a really nice way to remember this. It's going to be just f prime times g plus f times g prime. Okay, so not too bad. Basically, just derivative of one times the other, and then you add, whichever ones you didn't do the first time through. So the first function plus the derivative or times the derivative of the second. And again, this is usually best often shown as an example. So just for example, what if we have, given that y is equal to, let's do x squared plus x multiplied by 2x to the 7th minus x to the 5th. Let's do this. Okay, so let's determine dy dx, okay? And so a good strategy for this, right, is going to be to pick which of these functions you want to be your f and which of these functions you want to be your g. So, for example, let's just underline this one, and let's call this my f function. Let's say that's my f of x, and let's underline this next one to be my g of x function. I am being lazy, by the way. You know, technically you should write f of x and g of x, but since we're in a Calc 1 class where we really only have one input variable, and it's always going to be x, at least for right now, for our learning purposes, I'm just going to write f and g. So all we're going to do is we're going to use this this cool formula that we learned, and we will be done solving this problem. So basically, right, we already have two parts of it, which is really nice. We already know what g is, and we already know what f is. So we're really just missing f prime and g prime, essentially. So let's take a look at that. So f prime, right, is going to equal what? So we need the derivative of x squared plus x, and that's going to be 2x plus, now x to the first, right, x raised to the first power, we bring down the 1, we subtract 1 from the exponent, so that's going to leave us with 1x to the 0, but x to the 0 is just 1 itself, so actually this just leaves us with 1. That's not too bad. And then for g, right, so g prime is going to be, okay, so bring down the exponent, 7 times 2 is 14, x to the 6, right, subtract 1, and then minus, what do we get for the x to the 5th? We bring down that 5, so 5x to the 4th, and then we have it. There's our f prime, there's our g prime, and now we just plug things into our formula, which basically says, so, right, dy dx is going to equal, following this formula, we're going to have our f prime, which is 2x plus 1, times whatever g was, 2x to the 7th, minus x to the 5th, and then plus, right, plus, so now we're going to pop in whatever f was, and so f in this case was x squared plus x, and then whatever g prime is, which is 14x to the 6th minus 5x to the 4th. Fantastic, right? And at this point, right, this is the derivative. Now, in some cases, it's better to leave it like this. In some cases, it's better to multiply everything out and kind of simplify things. But for right now, just for the sake of learning, and just so that you can easily identify what's going on, I'm going to say that this is you know, the correct answer. Okay, so this is just fine. We have done the rule, and that's it. We've used the tool successfully. So let's do one more example. Let's do maybe a simpler example. So if, you know, y is equal to, let's do x squared plus 1 multiplied by x, I don't know, x minus 3 or something like that, right? Then, so y prime would equal, okay, so we need to, again, pick our f, which can be either one, but I'm just going to call the first one f. I'm going to call this one g, and then off to the side, we're going to need our f prime, right? We have a product of two functions, so f prime here is going to be 2x, and remember the derivative of any constant is always 0, because, you know, we, just as a reminder, we'll have 1x to the 0, and whenever we bring that 0 down, we're always just going to get 0 multiplied by stuff. So the derivative of a constant is always 0, so that's our f prime, and then for g, our g prime, right, the derivative of x is just going to be 1, and the derivative of the minus 3, or even just the 3 part, is still 0. So there's our derivatives, not so bad. And then using our formula again, we're just going to write down, so it's f prime, right, 2x, f prime times g, so x minus 3, and then it's going to be, so f prime times g plus, and then we have f, which is x squared plus 1 times g prime, which in this case is just 1, but I'll write it down anyway. So there we go. And now for this particular example, I'm going to multiply things together and simplify it just because it won't take too much effort. So if I multiply the first terms together, we're going to have 2x squared minus 6x, and then we're just going to have plus x squared plus 1. And I can simplify this, so 2x squared plus x squared combining like terms is 3x squared minus 6x, and then plus 1. Okay, so that's not too bad. This is going to be our derivative. Now, another reason that I decided to multiply this out is because I wanted to show you that, you know, even though we are using the product rule here, in this particular case, you know, some of you may be wondering, why didn't I just multiply these together and take the derivative that way? And that's a totally valid thing to do. So if we had x squared plus 1 times x minus 3, right? If I multiply these together using, some foiling, right, I'm going to get, let's see, so x cubed, and then minus 3x squared, then plus x, and then minus 3 for the last term. So really this function that we're taking the derivative of is x cubed minus 3x squared plus x minus 3. And now we can take the derivative just using the exponent rule that we learned about in the last video. And we'll see that the derivative of x cubed is indeed 3x squared. The derivative of 3x squared is going to be, minus, we're going to get a 6x. And the derivative of our last term, the plus x, is going to be a plus 1. And the derivative of the minus 3 bit, again, goes to 0. And you'll notice that these match perfectly. Okay, so this is just an example to show you that, yes, indeed, the product rule works, just like we intended, and life is all good. Okay, fantastic. So that is for, what to do if you have the product of two functions. I do want to highlight that right now we are dealing specifically with polynomial functions. We're going to need a little bit more background to deal with non-polynomial functions, things like, the derivatives of sine of x and, logarithms are going to come back and things like that. But for now, we're not going to focus on these. We're just going to get the basics of these rules down using some relatively simple polynomials just to build some repetition and get comfortable using the rules. That way, when we learn about these other functions, you're going to be like, oh, I already know how to do the product rule. I'll be fine. Okay? So the last bit for this particular video is how to take the derivative of the quotient of two functions. And so I'll write this down. So the quotient, or the quotient rule, okay? The quotient rule is similar to the product rule in the sense that we are tackling another scenario of how functions typically look like. So if I were to say, given y is equal to the quotient of two functions, f of x and g of x. Now, typically, I'm just going to pause here, right? That is a quotient of two functions. What I typically like to do for remembering this rule, so then we have the derivative is equal to, okay, I prefer, instead of calling these f of x and g of x, I found, courtesy of my high school math professor, shout out Mr. Randall, is that the top term I'm going to call the high term, and the bottom term I'm going to call the low term. And there's a fun little jingle for remembering this. So the derivative using of the quotient of something, or the derivative using the quotient rule, is low times the derivative of the high thing, so low d high, and then minus, then we do high times the derivative of the low thing, all over what we're going to call low, or low squared. And the jingle is really simple. It goes low d high minus high d low, all over low. And when I teach this in person in class, everybody always laughs at me because I make them do it. I make them say it with me. And I strongly suggest you pause the video and say this silly jingle out loud, because we had to do it and it has stuck with me ever since. And I think it's one of the best ways to remember the quotient rule. So it's low d high minus high d low, all over low. And if you want to see it in action, right, as an example, let's say, let's y equal, let's just make a random polynomial up. Let's just do x squared plus 6x on top. And then on the bottom, let's do 2x to the fifth minus 3. Okay, so again, I'm going to split these up. I'm going to call the top part here my high part. And I understand, right, that's not the correct English way of spelling the word high, but, just roll with it. And then, this bottom part I'm going to call my low part, okay? Now, in order to take this derivative, we're going to eventually need the derivative of the high part, so I might do that just to kind of prepare. So my d high, again, I'm not being very mathematically rigorous here. I'm just right. The derivative of the high part is going to equal 2x plus 6. And then my d low part, is going to equal, all right, so bring down that 5. We're going to get 10x to the 4th. And the derivative of a constant is just 0, so that's all we have. And so then we can just say, then, dy dx, the derivative of this function with respect to x, is going to be low d high minus high d low all over low low. So I'm going to write that down. We're going to do low 2x to the 5th minus 3, then times the derivative of what was on top, which we already have prepared, 2x plus 6. So there's my low d high, minus my high, which is going to be x squared plus 6x, times d low, which is going to be 10x to the 4th, and then all over low low, which for us is just going to end up being 2x to the 5th minus 3 quantity squared. And that right here is an application of doing the quotient rule. Okay, right, and this is the quotient rule in action. So if you have the ratio of two functions, in this case just dealing with two polynomial functions, we can use this particular pattern every single time and get the derivative. I do want to point out again that I'm not simplifying the top just for right now, but it will turn out in the future that sometimes it will be really nice for us to multiply things together and combine like terms and all of that jazz, and you'll probably end up seeing some of that on the homework. But for right now, just to kind of get the point across of how you apply this tool, I am trusting that you all passed algebra, and that if you were asked in a future problem that you could multiply out the like terms, or you could multiply things out and collect like terms, and simplify things as needed. But for right now, we're just learning this new rule for taking derivatives, which is the quotient rule. And I think this is where I'm going to leave this particular video, just kind of learning these two things. There is a way to kind of avoid the quotient rule sometimes, and unfortunately, you're not going to have all the tools you need to do it until you watch the next video, but I'll give you a slight, a sneak preview, which is, taking this particular function that we had, right? We had it written as a quotient, right? X squared plus 6x over 2x to the 5th minus 3. If you're really good at algebra, may notice that I could choose to write this as x squared plus 6x multiplied by 2x to the 5th minus 3 raised to what power? Well, if something's in the denominator, it has been raised to a negative power. So in this case, the negative first power. And now we have a version of the product rule. So we've turned this quotient into a product. The only downside here is that in the past, and by in the past I mean like 15 minutes ago in this video, when we did the product rule, right, and I identified that this is my f and that this other bit here maybe is my g, the thing is that when we identified this g function and took the derivative, we didn't have this exponent here, right? We just had a polynomial because we know how to take the derivative of these polynomial terms, right? I can take the derivative of that, I can take the derivative of that, no problem. But what we haven't learned how to do yet is, what do I do if I have a function inside of like another function, right? What happens, right? I have this -1 that's kind of guarding all of this stuff. Do I just take the derivative of the exponent part? Do I only do the exponent rule of that bit? Do I have to worry about the derivative of the stuff that's on the inside? Like what do I do? How do I tackle this? And as of this video, we don't have the tools to answer that question. But if you kind of want to move on to the next video, you're going to find out that the answer is going to be a little mix of both.